highly electron donating. And as a result, when you do electrophilic aromatic substitutions on phenols or on arrow ethers, like a methoxybenzene, it's sometimes hard to stop the reaction after a single addition. In other words, because the ring is strongly activated, there's not a big rate difference between the first, the second, and the third electrophilic substitution. And so in this case, you'll notice, look at what's happened. You end up with tribromophenol. That's the reaction that I told you is diagnostic for phenol. But also notice one thing, that after you add the initial bromine, let's say you add the para-bromo group, this bromine is ortho-para-directing, right? Because it's slightly deactivating, but it is ortho-para-directing. And yet, you don't get bromination here. It is the phenol that overwhelms the effect of the bromine. So the more strongly directing group is the one that affects the regiochemistry of the subsequent additions. So in other words, when you get the first bromine in there, you have para-bromophenol. Now, both groups are ortho-para-directing, but the hydroxy is a more electron-donating group, as you understand, and so it is this one that dominates the next two reactions, and so you get this kind of a product and not the bromines there. When the initial group that you introduce is strongly deactivating, like a nitro, then it kind of follows that any subsequent electrophilic aromatic substitution is going to be slower than the first. And so the first one is the fastest, second one is slower, and the third one is really, really slow because you have now two, not one, but two very strongly deactivating nitro groups. And that's reflected not only in the rates, but also in the conditions. Look at the conditions you need. To get that third nitro group on there, you have to kind of brutalize this compound at 120 degrees for 5 hours to get to TNT. Okay, so here, there's no ambiguity about the placement of the nitro group, right? Because the methyl group is ortho-para-directing, so you get the para-nitro-toluene. Now, at this point, this is meta-directing, this is ortho-para-directing. So these two positions are the only ones where you'd expect reactivity, because both groups, both the nitro and the methyl, point to these two carbon atoms. And so here, there is no issue of, what's more activating, what's more deactivating. You don't even need to worry about that. In point of fact, it is the activating groups that are going to dominate the regiochemistry, and that's for reasons that you should be able to understand just by writing the resonance structure. Now, the question arises quite naturally, what happens when you have two groups that are pointing at different carbon atoms? In other words, you have two groups on the ring already. One of them points to electrophilic aromatic substitution at one carbon, the other at the other. And predictably, that means that you get lousy selectivity. So if you have a methyl and a chlorine, for example, both of which are ortho-para-directing and roughly the same in terms of activating ability, or deactivating, the methyl slightly activating, the chlorine slightly deactivating, you end up getting a mix. And so in a situation like this, when you do the nitration, don't expect to see a single product because both groups are ortho-para-directing, so all carbon atoms are in play. Now, one thing that you may not appreciate, but this is something to remember, Friedel-Crafts acylation. Remember, that's the one that introduces a ketone. The Friedel-Crafts acylation reaction only succeeds with highly activated rings. So, in other words, if you try to do a Friedel-Crafts on a ring that has even a single deactivating group, it doesn't work well at all. In fact, essentially it doesn't work. So that means that the Friedel-Crafts will work on rings that have alkyl groups or methoxy groups or are completely unsubstituted, but typically will not work if you have even a single nitro or a single deactivating group. And so that's because the acylium ion is not a particularly strong electrophile compared to, say, NO2 plus. And so the Friedel-Crafts acylation reaction is kind of a dicey one. You need to have an activated ring where it doesn't succeed. So if you have only one meta director, it doesn't really work. Okay. So now let's talk a little bit about hydrogenation. This compound, which is called stilbene, will undergo hydrogenation under the normal conditions that we discussed when we talked about alkene chemistry. Remember when we talked about alkenes, we said that characteristic reaction was catalytic hydrogenation. Treat the alkene in the presence of finely divided metal, typically palladium, but also platinum, rhodium, nickel, cobalt, and so on. There are a number of metals that will do this, but typically palladium. The slash carbon just means that the finely divided metal is supported on essentially powdered charcoal. Okay, so when you buy this stuff, it looks like a bottle of charcoal. It's a very expensive bottle of charcoal because palladium ain't cheap. And so you put in a little spoonful of this into the reaction mixture with solvent, and you introduce hydrogen, let it go at room temperature, and the double bond gets saturated. So you end up picking up one molecule of hydrogen in this process. Now, under these conditions, you say that, well, look, I have all these double bonds, and I've got 3 double bonds here, 3 double bonds there, one in the middle. Why? Why is it only this one that gets hydrogenated when, in fact, I could have added 6 other molecules of H2 and completely saturated the system to make this cyclohexyl and this cyclohexyl? The answer to that is that the benzene ring is not a normal double bond, as you know. We talked about aromatic stabilization. Well, here's kind of a good indication of that. That if those were typical double bonds, sure, they'd undergo hydrogenation under these conditions, no problem. But they don't. And so that tells you that there is this very special stability associated with the benzene ring. Now, does that mean that you can't, under any circumstance, reduce a benzene ring? No, you can do it, but you need to really use different, harsher conditions. So saturating this double bond, that takes place very, very readily. You can do this on your bench top without pressure or anything. On the other hand, to get the benzene ring to saturate with a cyclohexane, you need to heat it up, and you need to use high pressure of hydrogen. So these reactions are typically done in a pressure vessel, a heated pressure vessel. This has got some hazard associated with it, so pressure vessels always have a little blow-up valve. So if the pressure ramps up too much, the valve pops and the whole thing doesn't explode. You do it behind the shield and so on. Now, it turns out that these conditions are necessary when you use nickel metal as a catalyst, but rhodium is a particularly very expensive metal, much more expensive than gold. This turns out to be a very good catalyst for saturating benzene rings. And if you use rhodium, you can do this reaction at room temperature, typically. You don't usually have to heat it up. So bottom line is, yes, you can hydrogenate a benzene ring, but under conditions that are very different from the hydrogenation of a regular alkene. What that means is that if you have a benzene ring and an alkene, what we did here, selective reaction at the alkene is never going to be a problem. Now, it turns out that this benzene hydrogenation is kind of useful because of the following. You cannot really stop the hydrogenation at the first or the second stage. And so the first stage is slow because you have to overcome the reactivity of the benzene ring, not of the aromaticity, lack of reactivity, the aromaticity of the benzene ring. But once you saturate one of these double bonds, now you no longer have an aromatic system. So the second one is faster, and the third one is also fast. So that means that it doesn't stop here, it doesn't stop there. Once you start the hydrogenation, this slow step then immediately gives you fast the last fully saturated product. Now, what I've shown here are the changes in enthalpy for each of these steps. And you'll notice that the first step is endothermic. And that's what you would expect, because it is the first step in which you are destroying the aromatic stabilization of benzene ring. Once you saturate that bond, no more benzene ring, no more aromaticity. And so this first step is endothermic. The second one and the third one are strongly exothermic. Now, let's just play a little game here. We can use these numbers, as it turns out, to estimate what the aromatic stabilization of benzene is. Here's how you do it. If benzene had no aromatic stabilization, okay, so let's just say that there was nothing, that benzene was just like a normal, regular alkene, then the hydrogenation of benzene, the enthalpy change, would be equal to 3 times, roughly, the enthalpy change of this step, right? Because it would be like a cyclohexene and another cyclohexene and another cyclohexene. So we could estimate that the enthalpy change going from here to there, if there was no aromatic stabilization, would be equal to 3 times this number, okay? But it's not. Actually, the enthalpy change is the sum of plus this minus that minus that. And so now we just compare. 3 times the enthalpy change for the last step is this many kcals per mole. That's what it would have been. That's your prediction if there was no such thing as aromatic stabilization. That's the change in enthalpy that you would expect. But in fact, when I sum those numbers, I have about minus 49 kcals per mole change in enthalpy. So this is what you have predicted if there's no aromatic stabilization. This is the reality. If I subtract these two numbers, then this is the enthalpy change that is not there. That is the estimate that you give for the aromatic stabilization. And so this is one way to say that, oh well, the aromatic stabilization of benzene is about 36 kcals per mole. Now, there are other ways you could have thought to estimate that, maybe come up with a bigger number or a smaller number. That's not what's important. What's important is not getting this number nailed to the third decimal figure. It's recognizing that it's a very large number. I mean, 30, 35, 36, whatever it is a very large number. And so what this tells you is something that we've been emphasizing all along, that yes, benzene is not a normal alkene at all. It has this very special property of aromaticity, and this is a good indication of that. So this just gives you one way to measure what that aromatic stabilization is. Okay, so I want to go through this chapter again. This is an important chapter for us because it introduces us to a new mode of chemical reactions, electrophilic aromatic substitution. Chem 272, we never saw anything like this. Okay, this is different. So this takes place with benzene and benzene derivatives. And when we say benzene derivatives, I mean recognize that if I have two fused aromatic rings like this, this is a fused aromatic system, that the same kinds of concepts and the same kind of reactivity that we described for benzene will apply also to naphthalene, and it will apply also to anthracene, which is this stuff, and it will apply to essentially every aromatic system. Now, of course, once I have anthracene or naphthalene or whatever, I can't talk about ortho and para, but I can certainly make predictions about where to expect electrophilic aromatic substitution by doing the same exercise that we did for benzene. Draw the charged intermediates, draw all the resonance structures, see which position leads to the largest number of stable resonance structures, and that will give you a very powerful prediction about what to expect in terms of regiochemistry of addition. There's one problem at the end of chapter 16 that asks you to do that for naphthalene. And so take a look at that. You'll see that there's really nothing different about that. Now, the problem with benzene is that it's been around for a while. In other words, people have known about this. And so the simple substituted benzenes have common names and are non-systematic. And we do need to know these, unfortunately. And so, you know, if somebody says phenol, you need to know what it is. If somebody says anisole, you need to know styrene and so on. And so you kind of need to remember these names. It's not something I'm going to ask on an exam, obviously, but you do need to know these so that every time you encounter phenol, you don't go looking for, you know, gee, what's phenol, wasting time, okay? So that's something you need to do. Now, there's another little bit of nomenclature here that is, to me, confusing, and I think the students too, and that is the difference between phenyl and benzyl. Phenyl is just the benzene ring. Benzyl is the phenyl plus a CH2. So in chapter 17, we're going to be talking about benzylic and allylic reactivity. So this will become a little bit easier to remember. But please remember, phenyl and benzyl ain't the same. Okay, let's talk a little bit about spectroscopy of the aromatic rings, or benzene ring. And since if it's just benzene, by the way, you don't have any functionality except for the double bond. And so you expect to see CC double bond absorption, and you do. You see it around 1600 and 1500. These are usually pretty sharp. Notice that these are lower frequencies than for alkenes, and that's because the bond order in benzene is not 2, it's 1.5. Remember what I said about resonance structures. If I average out the bond order for the two equivalent resonance structures, it turns out to be 2 plus 1 divided by 2. In other words, 3 divided by 2, or 1.5. So each one of those bonds in benzene is of identical length and of identical bond order, roughly 1.5. The real signature for a benzene ring is the proton NMR. The protons in benzene are strongly deshielded. They come out all the way at 7.4. If you have any kind of electron withdrawing substituent on the benzene ring, that would be reflected also in additional deshielding. And so the large chemical shifts are really characteristic of benzene and most aromatics. So whenever you see protons in the NMR region, they're around 7, the little light bulb needs to go off in your head, and you need to say, aha, benzene ring, or aromatic ring. Now, the reason you already know is that this is another example, as we saw for alkenes, of magnetic anisotropy. What the heck does that mean? It means that you have an induced magnetic field that is induced by the circulating pi electrons, in this case the pi electrons of benzene. In the case of benzene, that induced field augments the applied field in the region of the hydrogens. And so the green induced field adds to the red applied field from the magnet, and so these protons that are on the benzene ring experience a greater magnetic field than the one that you apply. And the interesting thing is that because the magnetic lines of force curve onto each other, that above and below the plane, actually green arrows subtract from the applied one. So if we put a proton here or a proton there, the prediction would be that that would be strongly shielded. In fact, it is. So I think there may be a question like that in the text, but I can give you an example. Say, well, how can you just put a proton there? Here's how you do it. You have a benzene ring. This is going to be a little bit strained, but you have a chain that kind of bridges over it. And so if you modulate if you pick the length of the chain such that it can't easily flip around, then all the protons that are here are held above and below the plane of the ring, and those protons are going to be highly shielded. And so yes, you can actually see this effect. It's not something that is postulated. You can actually experimentally observe that. So coupling constants are, as you would expect, 3-bond couplings are stronger than 4-bond, stronger than 5-bond. The trouble is that very often, if you have only 1 or 2 substituents on the benzene ring, that you have a lot of coupling going on, and so the spectra, even at high field, are sometimes not first order. And so picking apart those coupling constants very often is not easy. There's one case when it is easy, and that is when you have a paradise substituted aromatic where X and Y are different. And whenever you have this situation, then you see this thing that looks like looks sort of like a quartet. It's not a quartet, but it looks like one. If you see this thing that looks like a quartet that's out around 7 ppm, then again, the light bulb needs to go off in your head and say, boy, it's going to be a para-substituted aromatic. Benzoic protons are also deshielded for the same reason, that the methyl group is in the area of the induced magnetic field, where the induced field augments the applied one. C13, not much to say, except that remember that C13 is a really powerful tool for determining the presence of isomers, because it separates out, even for a benzene ring, each one of these carbon atoms has a different chemical shift and is observable as a separate line. And so if you have aromatic rings, you can typically see each and every aromatic carbon atom, which is really nice. Notice that the most deshielded of all is going to be the quaternary one here, where there's no hydrogen attached. And also, it's going to be the smallest peak. So remember that when you have C13 spectra, that the height of the peak is not, unlike proton, it's not related to the number of carbons. There are other factors that affect the height of that peak, and that peaks with no protons attached are usually pretty small, whereas this would be the biggest peak in the spectrum. Okay, I don't want to belabor the UV spectrum. We're probably not going to discuss UV as aromatics, but now let's go to electrophilic aromatic substitution, which is kind of the meat of this chapter. So this is a new kind of reactivity. Notice it is substitution. Okay, so we're not doing an addition. Typically, when we saw alkene chemistry last semester, we saw different kinds of reactions. But the characteristic reaction of just cyclohexene, for example, was the addition of bromine. So you have the alkene, you add bromine, you get a dibromide. Of course, that's not the only reaction. You also saw ozonolysis, right? So you treat the alkene with ozone, and then you end up cleaving the alkene. Here, you get a different reaction. Here, you get a substitution. So a hydrogen is substituted for an electrophile. And so this is not something we've ever seen before. And it's clearly not an addition reaction. The other thing that you notice is that you can take benzene and expose it to bromine. Reaction conditions that would have led to an immediate reaction with cyclohexene, but with benzene, nothing happens. There's no reaction until you add a catalyst. And so this reaction has to be catalyzed by a Lewis acid. Typically iron, bromide, aluminum halide, some kind of strong Lewis acid is necessary to catalyze the electrophilic aromatic substitution. This again is very different reactivity from what we've seen. What we said for bromine applies also to chlorine. Iodine, as it turns out, does not do this chemistry. There is a way to introduce iodine into benzene rings. We're going to see that later on. It uses a different kind of reaction. Now, the mechanism for each and every one of these electrophilic aromatic substitution reactions is exactly the same. And so what it involves is generation of a reactive electrophile that then reacts with the benzene ring, destroying the aromaticity, creating a stable, relatively stable intermediate, which is charged, and then loss of a proton to restore the aromaticity. So the iron bromide manages to catalyze this reaction by weakening this bromine-bromine bond and polarizing it. Okay, so this electron pair gets donated to the iron, inducing a positive charge here and a positive charge there, which then weakens this bond and allows this reaction to take place to give you this charged intermediate. Now the charged intermediate is resonance stabilized. When I say resonance stabilized, please understand it's not nearly as stable as the benzene ring that gave rise to it. The benzene ring has about 36 kcals per mole of aromatic stabilization. You lost that, or most of it, when you broke that ring. And so the first step in the electrophilic aromatic substitution is the slow step. So forming this intermediate is the slow step. Loss of the proton to restore aromaticity is the fast second step. So the reaction takes place in two steps. First slow step to form that charged intermediate, fast step to restore aromatic stabilization. So this is going to be the fast step where you lose the proton and you're back at an aromatic system. Now, what never happens is you don't get addition. And the reason you never get addition is because the loss of the proton is always going to be faster, because with addition you don't get an aromatic ring back. Okay, so if you were to do the addition, you would get no aromatic ring. Okay, so all of the reactions that we discussed in this chapter follow exactly the same paradigm. We made a point of talking about nitration, not only because nitration is important, but also because the mechanism seems a little bit bizarre. That you have nitric acid, which we think of as a strong acid because it is a strong acid, but by itself it doesn't react with benzene. You need to catalyze this reaction with an even stronger acid, namely sulfuric acid, which protonates the nitric acid. So nitric acid acts as a base in the presence of sulfuric acid. Something that seems a little bit strange to us, but the difference in pKa's should reveal that. So you get a proton transfer. Once you get the proton transfer, you can dehydrate this intermediate to give you the active electrophile, which is NO2 plus or nitronium. So this is the electrophile. This is the electrophile that reacts with the benzene ring, and it gives you this charged intermediate, which loses a proton and gives you nitrobenzene. So it's no different from the bromination. The only difference is how you generate the nitronium ion. So the nitronium ion is generated again from nitric acid by protonation and dehydration. Okay, so sulfonation is kind of the same thing. The reagent used is fuming sulfuric acid, which is just sulfuric acid with sulfur trioxide dissolved in it. The reaction is every bit the same as what we saw. You form either the protonated SO3 or SO3 by itself, an adequate electrophile, you get the charged intermediate, loss of a proton, and so on. The interesting thing about these, and this, by the way, is these kinds of sulfonic acids, they're weaker acids than sulfuric acid, but they are still very strong acids. These kinds of acids are very useful catalysts in organic chemistry for the following reason. Sulfuric acid is not soluble in organic solvents, but benzene sulfonic acid is. And so you can use these as strong Bronsted acid catalysts in organic solvents. So these are useful. Now, the one thing that is interesting about these sulfonic acids is that the process can be reversed by adding water. So you can actually go back from here to the benzene ring and sulfuric acid just by adding water. That led us to the Friedel-Crafts alkylation reaction, which involved use of an alkyl halide, typically alkyl chloride or bromide, and aluminum trichloride. We said that the Friedel-Crafts alkylation had a limitation. The limitation was that if you have anything bigger than ethyl, like a butyl, that you end up getting skeletal rearrangements, which is always the signature of what? The signature of a carbocation. And so the Friedel-Crafts alkylation is still useful, but not for straight chain alkyl groups. So now you can ask yourself a question. Gee, I want to go from benzene to N-butylbenzene, so I want this product, and I want to go from here to there without getting this. Is there a way to do that? The answer to that is yes, there is. And you can probably figure it out. That's not an easy problem for you at this stage, but you actually know all the steps that you would need to do that. I'll give you a hint. You want to do a Friedel-Crafts acylation in the first step. Okay? So So the reason you get the branched intermediates is because you get a rearrangement, in this case involving a hydride transfer to get to the secondary cations. Nothing particularly surprising about that. Now the other problem with the Friedel-Crafts alkylation is that the alkyl groups are activating. And so that means that each subsequent alkylation is faster than the preceding one. And so you would expect then that if I'm going to do Friedel-Crafts alkylation, I got a problem. Because I'm going to get an alkylation and a fast one, a fast one, a fast one, and pretty soon I'm going to end up with, you know, a real mixture of alkyl benzenes that's going to be useless and very difficult to separate. So how do I stop it after the first one? The way you do that is the same way as always. If the second alkylation is faster, then you want to always make sure that this is present in low concentration. And so the way you do that is you use a big excess of benzene. And so once you get the first alkylation, then you still will have methyl chloride, but there'll be a lot more benzene than toluene. And so the chances are that the methyl chloride is going to react with another benzene, which is there in high concentration, and that won't react with a toluene, which is there in low concentration. Makes sense. So that's how you control that. Now, is that practical? Yeah, sometimes. Any way you generate a cation, by the way, is fine. You can generate a cation any old way you want, and you can still get a Friedel-Crafts alkylation. So which ways do we know for generating cations? Well, one of the ways we talked about when we talked about alkene chemistry was to take an alkene and allow it to react with a strong Bronsted acid. The alkene gets protonated, you get a cation. That should react as a Friedel-Crafts reagent. Surely it does. And so that works really well. Now, the Friedel-Crafts acylation is probably a little more useful. Even though it doesn't work when the benzene ring is deactivated, it's still more useful. It gives you a carbon-carbon bond, as does the Friedel-Crafts alkylation, but it also gives you functionality. It gives you this carbonous ketone. And so, unlike the alkylation reaction, the Friedel-Crafts acylation needs stoichiometric aluminum chloride. The reason for that is that the product is a stronger base than the starting material. And so the aluminum chloride is going to be tied up, if you will, by the product. So once you form product, it's going to take catalyst out of circulation, which means you can't use it in substoichiometric amount. You need a full equivalent. And so that's one, call it a limitation, because you don't get this as your product. What you get is the Lewis base, Lewis acid conjugate that then has to be decomposed with water and work up. The way this works is, we showed that this morning, is you form this acylium ion. The acylium ion is formed in the same way that you form the carbocation from the Friedel-Crafts. And this is resonance stabilized, and it can react with activated benzene rings, and you end up getting these ketones. The nice thing is you can do it intramolecularly. This turns out to be really useful. Now, one big advantage with the acylation, that's sort of the other side of the coin. The disadvantage was what? That it doesn't work with deactivated rings. The advantage, other side of the coin, is that because of that, you don't get polyacylation. That first acyl group deactivates the ring enough so that the second Friedel-Crafts doesn't take place. It only takes place once. And so you don't need to worry about multiple products. Then we talked about directing effects. And here is where we need to actually get some experience pushing arrows. And so if you have not a benzene ring, but a ring that already has a substituent on it, then you notice that this substituent directs the nitro group to be either ortho or para, and you hardly get any meta product, right? It's a tiny amount. And so we need to understand why that is. Now there's a general rule. The general rule is that activating groups and the halogens will direct ortho para. Deactivating groups like nitro, sulfone, acyl, whatever, those will direct meta. So if it's activating, which means electron donating, then ortho-para. Deactivating, meta. you can see this with the nitro. Nitro is electron withdrawing, deactivating, you get meta addition. The reason for this we discussed, and that was that you end up generating a reactive intermediate for the nitro that, in the case of the meta position, gives you these three resonance structures. If you compare those to the resonance structures that you get with para addition, you'll notice that one of them, this one here, the red one, is going to place a positive charge on the carbon that is directly attached to the positively charged nitrogen. And so, for colloidal reasons, this particular resonance structure is unimportant. If it's unimportant, then remember what that means. It means that the structure of the intermediate is a weighted average, but that this structure really is not given much weight at all, which means that this particular charged intermediate it has only 2 resonance contributors, whereas this one has 3. The greater the number of resonance contributors, the greater the stability, because you get more bonding. And so this is a more stable intermediate than this one. And so that's why the nitro group is meta-directing and not ortho-para. For the ortho position, it's the same situation, so you don't need to, well, you can write down, you can write the intermediates, but it won't change anything. So, so that's why the nitro group is going to be meta-directing and not ortho-para-directing, because when you get meta-addition, you have the maximum number of resonance structures contributing to the stability. Now, when you have an ortho-para-directing group like methoxy, which is a very powerful ortho-para-director, the reason is similar, but a little bit different. Here you have one additional resonance structure, and this turns out to be a very important one because, as you told me last time, every atom in this structure has a complete octet. And so not only do you get more resonance structures for ortho-para than you do for meta, but you also get this very good one that is important. And so you can convince yourselves that the meta addition, or for here, gives you one less. Now, writing these resonance structures should not terrify you at all. You should be able to, by now, write these fearlessly. And so if I have an electrophile, and I want to show this as giving you a meta adduct, then I should be able to just, by the way, don't forget that there's a hydrogen here, okay? We don't show these hydrogens, but when you write the mechanism, it's always a good idea to put those in so you don't forget about them, at least now. So here's the meta adduct that I formed from the electrophilic aromatic substitution. Now this is the one that is going to give me fewer resonance structures. So how do I write these? Well, I just push arrows in the normal way. You've seen us, you've done this now umpteen times, right? And so it really shouldn't in any way be foreign to you. And so I can push arrows in this way to distribute that positive charge to 3 positions in the ring. But you'll notice that what I cannot do with the meta adduct, which is what I could do with the ortho-para, is I can't involve the non-bonding electron pairs on oxygen. The non-bonding electron pairs on oxygen for meta addition don't get into the act, okay? And so, so that limits the resonance structures to 3 and not 4, and that affects the nuclear chemistry. Okay, so so when we talk about activating and deactivating groups on the benzene ring, you always have to ask yourselves, activating compared to what? Activating compared to benzene, as usual. So that brought us to today's lecture, where we talked about deactivating groups, making it possible to isolate the individual products. If you have activating groups, then typically you can get poly substitution. And then we talked about hydrogenation and so on. So that wraps it up for chapter 16, which was our first chapter of aromatic chemistry. Now, as it turns out, there's a lot more to learn about aromatic chemistry, and we're going to talk about some of that in chapter 17, which will start momentarily. Please stop texting. Thank you. And also later on, when we talk about the chemistry of aromatic amines. Chemistry of aromatic amines turns out to be particularly interesting because it allows us to do some things with aromatic substitution that you absolutely positively can't do any other way. So let's start briefly on chapter 17 today, see how far we get. I mentioned that this was going to be a chapter on allylic and benzylic reactivity. And so the first thing that you will think about is what? Is, why make a distinction? I mean, what's so special? Why do we need a special topic of benzylic and allylic reactivity? Can't we just talk about benzene rings? Can't we just talk about, double bonds? The answer is, well, yeah, you can, but there's a special reactivity that's associated with allylic hydrogens. And remember, allylic ones are the ones that are at the position once removed from the double bond. So we're not talking about the hydrogens that are bonded to the vinyl group. We're talking about the ones that are one away. So this will be the allylics. We also will talk about an allylic halide. This is an allylic halide. Now, if the chlorine were attached here, that would not be allylic. Benzylic are going to be, this is a benzylic bromide, which as it turns out is very reactive. And these are benzylic hydrogens, which also have kind of a special reactivity. This would be a benzylic hydroxy. You say that, but wait, this isn't a benzene ring. And you're right, it's not. It's a naphthalene ring. But we still will call that a benzylic hydroxy, okay? So if it is alpha to a aromatic ring, it is benzylic. So if it is a carbon, if it's bonded to a carbon, it's bonded to an aromatic ring, any aromatic ring, whether it's naphthalene, whichever, then that's going to be benzylic. So why do we bother to make this distinction? Well, we kind of know why that is. The reason we make a distinction here is because the benzylic and the allylic bromines, hydrogens, hydroxy groups, whatever, don't react the same as non-benzylic and non-allylic. They have different reactivity. And so it makes sense to do that. Now, why is that? Well, resonance stabilization of the intermediate is the short answer. And so allylic and benzylic carbocations, allylic and benzylic carbanions, allylic and benzylic radicals are all stabilized through resonance compared to what? Compared to non-allylic, non-benzylic carbocations, radicals, carbanions. So whenever we say stabilized, remember, you need to say compared to what? Okay, so this comes, I hope there's no big surprise. We have talked about, chapter 72, we've talked about allylic resonance. And so I'm not going to push arrows here, I'll let you do that, but you know that if you have an allylic carbocation like so, that the positive charge is going to be distributed at the end carbons. The middle carbon doesn't have a positive charge, but the end two carbons share that positive charge. And so if I average out these structures, it tells me that the two end carbons have plus 1/2 charge. With the benzylic system, it's a little more complicated. The benzylic system, I can push arrows. I'll let you do that. I'm not going to do that here. But I can distribute this positive charge to the two ortho and the para carbon atoms. And so that means that when I have a benzylic carbocation, the positive charge is not exclusively on the benzylic carbon, but it is actually delocalized into the aromatic ring. And so that means that, and this is the take-home, that reactions that proceed by means of allylic or benzylic carbocations, carbanions, radicals will take place faster than ones that don't. Because the intermediate that you form is going to be more stable. And through Hammond's postulate, the more stable intermediate will be formed faster than the one that is less stable. And so it kind of makes sense. Now, let's see, is there experimental verification of what I just said? The answer is, yeah, there is actually. And the way you look at it is you look at the rates for solvolysis. Solvolysis, remember, was an SN1 reaction, where you take an alkyl halide, typically, and you dissolve it up in some solvent that is polar and that can react with the cation. Typically, what is that? Methanol, ethanol, right? And so in this case, it's solvolysis in ethanol, aqueous ethanol. And so you look at the rate for disappearance of the alkyl chloride. And so you compare these three. So here you have a tertiary alkyl chloride. Now we already know that tertiary alkyl halides are reactive in SN1 reactions, right? Those will undergo SN1 reaction quickly in solvents that are polar, hydrogen bonding. And so that's what you see. This is fast. Now, if I just put a double bond here, then it's about 160 times faster. And so that tells you that just placing that double bond, making this from an alkyl to an allylic, is going to greatly accelerate that. Why is that? Well, the reason for that is the one that you know. That the intermediate that you form, that cation, is going to be much more stable now, because not only is it tertiary, but it's also allylic. And it turns out that you can see for primary allylic cations, for primary allylic halides, you see a big rate acceleration relative to the tertiary. So even though this is primary and that's tertiary, this one's still faster. It's faster because it's allylic. Now, you also should notice that this and this give rise to the same allylic cation. Okay? So solvolysis here, solvolysis there, give rise to exactly the same intermediate. And then you need to think about, well, gee, if it's the same intermediate, then why is this one faster than that one? And figure it out. Okay. So benzylic, same thing. But look at the relative rates. Holy cow! You know, you start with the secondary benzylic halide, then you go to a tertiary benzylic halide. Once you put 3 phenyl groups there, you essentially can't measure the difference in rate here. It's too big to measure. So this is far, far more reactive than even this secondary benzylic halide, which is reactive. And you'll notice changing a methyl for phenyl makes a big difference too. Why is that? Well, because when you add the second phenyl, I can delocalize that positive charge not into one benzene ring, but into 2. And so the trend in reactivity is the one that you would predict based on the total number of resonance structures. And the more resonance structures that you can write, the more stable intermediate, the faster it is to form the cation. And so you can imagine that you can play, now that you know about electrophilic aromatic substitution and all that, you can play the game even more. Put an electron donating group on one of the phenols. And so in other words, I can take, where is it? I guess I don't have it. Yeah, this one here. Let's just take this compound, instead of benzene, put a methoxybenzene. And now the positive charge can be delocalized all the way into that oxygen atom. You can form this nice charged intermediate where all the atoms have a complete octet. And so the prediction you would make, and you'd be right, is that the solvolysis to form this cation is going to be much, much, much faster than to form that one. And that's correct. So none of this should come as any surprise, right? I mean, you know something about aromatic stabilization, you know something about resonance stability, and so all of this kind of follows, I think, logical progression. Now, we said something about, solvolysis here. We said about solvolysis there. These are solvolysis rates. these are solvolysis rates, but we didn't really say anything about the structures of the products, okay? So now let's talk a little bit about what kind of products to expect. Again, this is all common sense. So if I take this primary allylic chloride and I do a solvolysis reaction, then the first step, which is the slow step, is going to be to form the cation. Okay, so I'm going to get this allylic cation. But the allylic cation, as you know, is resonance stabilized, which means that the two end carbons are going to share that positive charge. Now, because this is not a symmetrical allylic cation, it doesn't mean that these two end carbons, this one and this one, this one and this one, it doesn't mean that these two end carbons are going to share that positive charge equally. No. It tells you, of course, because this one is tertiary, there's going to be a slight excess of positive charge here relative to there. And so this is going to be the more important resonance contributor, and so the positive charge is going to be localized to a greater degree at this carbon over that one. And when the nucleophile, in this case water, intercepts that carbocation, then you're going to get two products, these two, and notice that the ratio reflects the difference in stability at the two ends of the carbocation. So up to here, it all makes sense. You get a solvolysis reaction, you get a carbocation. The carbocation is resonance stabilized, you have two resonance contributors, one is more important. Guess what? Most of the product comes from the most important carbocation. No surprise. Now, the benzylic cations, the one thing to remember is that you only ever get one product. You only ever get that product, okay? So if I have the tertiary, I haven't shown the tertiary chloride. So if you have a tertiary chloride, bromide, iodide, you name it, it undergoes solvolysis. You get the benzylic cation. The benzylic cation is delocalized here to there, and there's one more that I didn't show. And so you can say that, well, geez, you know, I got positive charge on this carbon, I got positive charge on the orbital carbons, I got positive charge there. How come I don't see these two as products? And this is the only product. Well, you know why you don't, because those are non-aromatic, which means that they're far higher in energy, at least 30, 35 kcals per mole higher in energy than the non-aromatic ones. Okay, so we've gone a little bit over.